Let us talk about this problem. We are given a sorted array and a number x. We need to find out if there is a triplet in the sorted array whose sum is equal to x. We need to return true if there is a triplet, otherwise we need to return false. Let's understand with this example. We are having a sorted array and we have a number 32. If you take a look at this array, we have a triplet 4, 8 and 20 whose sum is 32. So our answer is true. If you see this example, we are given the sorted array and the number x is 14. So there is no triplet with sum 14. Even the largest sum is more than 14. So our output is false. Now please pause this video and try to think of a solution that takes an array as input, number x as input, returns true if there is a triplet, otherwise returns false. Let us first talk about a naive solution to solve the problem. The idea is simple. We are going to consider every possible triplet. For every triplet, we are going to check if its sum is equal to x. If it's equal to x, we are going to return true. And after considering every triplet, if we never found a triplet with sum x, we return false at the end. So we are going to pick the first element from index 0 to n minus 3, right? Because we are picking this way. The first element is picked, then second element is picked as every element on right of it. Then third element is picked as every element on right of second element, right? So the first element's index is never going to go beyond n minus 3, right? Because there should be two elements after it. The second element is picked as every element on right of it, right of first element. The third element is picked as right of second element. And if we find a triplet whose sum is equal to x, we return true. Let's do a dry run for this example. So we have the sum as 20 and we have a triplet 2 plus 3 plus 15 as sum 20, right? So we pick I2 as the as one element and we are going to consider every triplet where 2 is an element, right? So we are going to run for j equal to 1. Then when we are at j equal to 1, we are going to run from k equal to 2, right? So we have this triplet as the current triplet. His sum is 10. It's not 20. So we move ahead. We consider k as 3. 2 plus 3, 6. 2 plus 3, 5 plus 6, 11. Right? Not 20. Then we consider 15. 2 plus 3 plus 15. We get the triplet. We return true. Right? And suppose you are given an element, say, whose value is even greater than the largest triplet or any sum who's not present in the array, then you will come out and you will return false. What is the time complexity of it? It's clearly big O of n cube. Auxiliary space is clearly big O of 1. Now please pause this video and try to write down a solution which works in time complexity better than big O of n cube. Before we talk about the efficient solution, I would strongly recommend you guys to try this yourself because it's going to be using the two-pointer approach. It's going to be using the the pair sum problem as a subroutine. And the expected time complexity is big O of n square and big O of 1 auxiliary space. So please pause this video and with this hint, try writing the complete solution yourself. Here is the complete approach. We traverse the array from left to right. For every element, we consider this as one element of the triplet. And we find the remaining two elements in the array on the right side of current element. And for finding the two elements, we pass the sum as 32 minus current value. X is 32. So we begin from here, right? We begin from 2. And what we do is we consider 2 as one element. And then we try to figure out if there is a pair in the array on right side of it with sum as 32 minus 2, 30, right? In this array, right? If we find a pair with sum 30 in this subarray, then there is a triplet with sum 32 where one element is 2, right? That's what we do. So with 2, we do not find a pair with sum 30. There is no pair with sum 30 in this subarray. So we move ahead to the next element. We traverse the array from left to right. Now we come to 3. When we come to 3, we find out if there is a pair on right side of 3 with sum 32 minus 3, which is 29. So there is a pair with sum 29, that's a pair, right? So is pair is being used as a subroutine, right? And this function returns a true this time. So we find a pair with sum 29, we return true, right? And triplet first element or the one element of this triplet is 3 and we picked this element here. For remaining two elements, we simply called is pair sum. But when you are calling is pair sum, you need to pass starting index as an extra parameter because this pair sum is going to search in the whole array by default. So that's the extra thing we are going to pass in the is pair sum. We are going to pass the starting index, and is pair sum is going to begin from that index, and then it's going to follow the normal routine. So that's the simple idea. Now I have given you enough hints and you can write the complete code yourself for sure. Here is implementation of the efficient approach. I have written more of C++ style code. Java code is also very close. We just need to make few changes. Instead of bool, we need to use boolean, right? And we don't need to pass size of the arrays in argument that we can get using arr.length. Rest of the code is same in both C++ and Java. So what are we doing in this code? We have this main function is triplet that takes an array, size of the array, and x as arguments. And what it does, it traverses from 0 to n-3. See, why are we going till n-3? We have already discussed that because we are considering this element as first and we are going on right side of it. So when you go on right side of it, there should be at least 2 elements after it to have a triplet. That's why we are going from 0 to n-3. And we are simply calling is pair. Is pair we have already discussed. The only difference here in this is pair implementation is we have an additional parameter starting index, and I is initialized as starting index instead of 0. In normal is pair, it was initialized as 0. So what we do, we call is pair for ARR and sum as x minus ARRi and starting index as I plus 1. Basically on the right side and sum reduced. Let's now see a dry run. So when we have this array and x is 33, we'll begin with 2, I is 0 initially. Then we'll call is pair for this and sum will be reduced as 33 minus 2, 31. So sum is 31, right? And index, starting index is 1. And in this sub-array, we look for pair where sum equal to 31. We don't find a pair. So this function called returns false. When this returns false, we go to the next iteration, right? In the next iteration, we have this value as 5, right? We call for right side of it with sum 33 minus 5, 28, right? And this time we find a pair with sum 28. The pair is 10 and 18. So this function returns true. And as soon as this function returns true, we immediately return true, right? We don't proceed further. So we return true from this function. We find the triplet with sum 33. So this is the simple implementation. The time complexity is clearly big O of n square, big O of n loop here, and then big O of n loop here, and auxiliary space is clearly big O of 1. Now one interesting thing about this solution is, even if you are given an unsorted array, then also the time complexity is going to be big O of n square only. Why? Because we can simply sort the array in big O of n log n time first. Right? I'll sort the array first. In is triplet function, I'll simply call sort function and I'll sort the array, right? And after sorting, I can write the same code and overall time complexity is going to be big O of n log n plus big O of n square, which is nothing but big O of n square only. So overall time complexity or upper bound on the time complexity remains O of n square even if you have unsorted array. So this is the idea. It gives you big O of n square solution for both sorted and unsorted. In case of unsorted, you just need to sort the array first.